Hello, thanks for introducing me. And I would like to start my presentation from a historical note. The very first version of ACD-pKa algorithm was introduced back in 1997. And it has been the industry standard for over 25 years now. And obviously, throughout all these years, the algorithm hasn't remained static. As R&D projects are constantly pushing the boundaries and move to novel, previously unexplored regions of chemical space, we must adapt to that in order to stay competitive. And therefore, our algorithm is also constantly evolving. And a major aspect of this evolution is experimental data. It is well known that any predictive model can only be as good as the data that it is based on. And any attempts of improvement of the model inevitably involves a quest for new data. Therefore, since 2006, ACDLabs has actively sought data sharing collaborations with top pharma and chemical companies that would benefit all users. And now let's dig into a bit more detail about how these collaborations actually work and how we can offer the benefits to all users. So obviously, these projects start with us receiving curated experimental pKa data for in-house compounds from our partners. On our side, we incorporate this data into the algorithm. The pKa algorithm is based on Hammett-Taft equations. So basically what we do is reparameterizing old equations based on new data. And we can also construct new equations. And during this process, the chemical structures are decomposed into the ionizable centers, the substituents, and so on. The final algorithm is eventually just that, a set of equations that does not contain the full structural information. And the key point here is that when the data are incorporated into the model, proprietary information is not exposed. And as a result, the updated model is specifically adapted to the partner's needs, so that the partner who shared the data gets an immediate benefit in terms of significantly increased prediction accuracy for their in-house compounds. But since no proprietary information is involved, we can also offer the same model to the entire user community, so that everybody else gets the same model, a generally better model with increased chemical space coverage. So now we can move to our latest developments that are available in our latest release of Percepta software, which is now version 2023. And the discussed pKa data collaborations are a major part of this release. But aside from that, ACD-pKa classic algorithm has seen a series of conceptual upgrades in this release. And these upgrades are significant enough so we can actually call this a new generation algorithm. So let's now walk through the updates in detail. So going back to the data, the collaborative projects resulted in acquisition of about 3,500 proprietary molecules that cover a diverse range of both chemical structures and application areas. So as you can see on the slide, there are pharmaceuticals, high production volume industrials, agrochemicals, and so on. And after the expansion, the overall training set now contains about 25,000 compounds with more than 40,000 individual pKa values. And as I have mentioned before, these data allowed us to reparameterize a lot of existing Hammett-Taft equations and also create new ones. And actually, the quality and quantity of new data in the updated training set was enough to cover a series of new ionization centers that were previously unrecognized by the software. Some examples of such ionizable centers are provided in this slide. So previously, these had no prediction. These were not recognized as ionizable centers. Now we have enough data to actually output a reasonable pKa values for these compounds. So these involve certain kinds of acidic carbon centers, some more exotic nitrogen atoms, as well as organophosphorus acids, and so on. These are just examples. And apart from identification of ionization centers and getting accurate pKa predictions for them, another big aspect is calculation speed, which is directly related to the complexity of ionization graph. So our goal is to predict the so-called macroscopic or apparent pKa values, which is the predicted analog of experimental pKa. And the most accurate approach for calculation of these apparent pKas is running the simulation that includes all microscopic pKa stages, that is, the values for all individual dissociation steps in the graph. And here our example molecule is the amino acid cysteine that has 2 acidic and 1 basic center, so 3 centers overall. As you can see on this slide, the full ionization graph is already quite involved. And the complexity of calculations here grows exponentially with the number of protons. So when the molecules become more complex and the number of ionization centers grows bigger, the calculations can become really slow. And in fact, in the past, it was a common complaint from the users that pKa calculations are slow. So this definitely needed to change. And the key to addressing this issue in the current release was the fact that in the absolute majority of cases, in fact, only a single deprotonation pathway plays the major role in determining the macro pKa. And in this example, it is the pathway highlighted in green and bold arrows. But before we get to that, I should start mentioning the changes related to speed from the fact that the micro pKa calculation procedure itself has been optimized. And this optimization alone is enough for a 20 to 30% increase in prediction speed. But then, when we developed a special optimization procedure allowing to reduce the number of micro pKa constant used in the simulation, to limit them only to those associated with the key pathways, together with the first point, it led to overall up to 5 or in some cases even 10-fold increase in speed. So that is the real big thing. And apart from that, simplifying the simulation gives another advantage, that it helped to resolve a rare but pretty annoying issue where dissociation stages could sometimes be wrongly assigned as acidic or basic. So essentially they could be mislabeled. So now when we have only the key pathways, that issue is gone. And fortunately, there's also no compromise in prediction accuracy, because any minor loss of accuracy that is inevitable when you start using the simplified simulation is far outweighed by the overall gain of accuracy resulting from the retrained algorithm. So now we have covered what has been done for the new release. So now let's move to evaluating the results of the predictions in Percepta version 2023. So if we take a look at the new training set compounds in this release, of the entire 3,500 compounds, there is a clearly identifiable subset of novel compounds which turned out to be really problematic for the old algorithm. There are about 400 molecules overall that are outside of applicability domain of the old model. And if we look at the histogram that groups the number of predictions falling within different buckets of accuracy, we can see that before training, so we are looking at the light bars, only about 1/3 of compounds received good predictions that are within half log unit of measured values. And almost half of the compounds were seriously mispredicted. So they got prediction errors more than 1 log unit on average. But after training, and now we are looking at the dark bars, the situation improved very significantly. So basically now we get good predictions for about 80% of the compounds, and there are no very strong outliers. Basically, everything fits within the 1 log unit bucket. But this only shows that the training obviously worked. And of course, we would like to see a more real-world example of how predictions became better. And for that purpose, we tried to reproduce an evaluation study that was published in Molecular Informatics journal a few years ago. The authors of that study also did an evaluation, and this involved both their proprietary compounds and public compounds. So we can obviously try to reproduce only the public part, but this time using our new updated algorithm. The public data set they used came from a compilation by Vertex Pharmaceuticals. Originally, it involved about 600 compounds collected from 4 literature sources. And the authors of the evaluation study referred to it as one of the best, one of the most diverse and large publicly available data sets for pKa prediction benchmarking. Starting from the entire set, we try to reproduce the same data processing procedures, removing non-drug-like compounds that are basically too small, the compounds which, after stripping stereo information, become duplicates or excessively similar to each other. And finally, we arrived at a data set of about 400 data points, with the ratio of bases to acids at about 3:1, which is a good indication of the real distribution of compounds in pharmaceutical data sets, as bases clearly prevail there. So now if we look at the predictions before and after training, so the results before training correspond to Percepta version 2022 and earlier. And as we can see on this slide, the actual agreement between experimental and predicted pKa values in general is not that bad, especially for acids, but the statistics are ruined by certain strong outliers in both acid and base plots. And in base plots, we also see a kind of arc in the plot, which corresponds to systematic deviations seen for certain ionizable groups. But after training, the situation noticeably improved. Now we get R² of about 0.9 for bases and 0.95 for acids. Mean absolute error of prediction is less than half log units in both cases. And there are almost no strong outliers after the training. And if we look at this data for acids and bases combined, so we take the entire set of about 400 data points, we can see that the mean absolute error of prediction has gone down from 0.7 to 0.4 units. And I've run these predictions through Percepta batch application, which also outputs calculation speed. And if we look at these numbers, we can see that we have gone up from 11 structures per second in the previous version to almost 25 structures per second in the new release, which corresponds to about 2.5 times increase. And we can see that we only have an average of about 3 acidic hydrogens per molecule in this data set. And as the speed difference grows exponentially with number of protons, now we can easily see how we can arrive at the advertised 5 to 10 times increase in speed. Because if the data set involves more complex molecules, such as molecules with carbohydrate groups attached, or macrolides with a number of peptidic fragments, the complexity of calculations will be much higher. So these kind of numbers will definitely be achievable. Okay, so now we covered the improvements of pKa, but predicting pKa alone is not enough. First of all, often it is necessary to analyze the distribution of charged species in the solution, not just the pKa. And then there is also a number of pH-dependent properties, such as pH profile of octanol water distribution log D, or solubility log S, and so on. And when we compare predictions for pKa and for these derived properties, there are a few important points to consider. First of all, quite obviously, improved pKa prediction accuracy directly applies to all of those related properties. But what's not so obvious is that, unfortunately, the speed gain does not automatically carry over, because the derived properties still use the full simulation. And usually, in terms of accuracy, full simulation is worth the hassle. But unfortunately, it also has its downsides. Specifically, that predictions now accumulate the additional so-called normalization error. In the scope of this presentation, I won't go deep into technical details about that. But the basic idea is that the full ionization graph has some level of redundancy of information for extracting charge distribution data. And also the micro pKa constants themselves are also inexact. They are predicted with some error. And in order for the final numbers to make sense, they need to undergo an additional round of optimization to produce, as we call them, normalized values. And this may cause some confusion in the final results. And probably this is best illustrated by an example. So in this example, we have a really simple compound, chlorpromazine. It has only two basic ionizable centers. The top ionization pathway is the preferable one. Only one pKa constant of 9.4 is practically relevant. And as the pKa's are far apart, this micro constant of 9.4 actually corresponds to the apparent pKa. So the numbers in bold are the original predicted micro pKa constant. And the numbers in italics are the values after normalization. You can see that the difference isn't really huge, but when we switch to the prediction of derived properties, and we try to compare the numbers predicted from the simulation in the program, and manually calculating, for example, log D, taking just the pKa, the macroscopic pKa value, and log P through the Henderson-Hasselbalch equation, we see some difference. For log D, the differences are also not very big. Basically, everything that is color labeled on this slide is just everything that is bigger than the rounding error. But if we take a look at the distribution of ionized forms, and specifically in this table, we have positive form fraction at various pH values near the inflection point, near the pKa value, we can see that there is a deviation by a few percentage points between the numbers calculated directly from pKa and the numbers from simulation in the previous software version. So as I have mentioned before, this often comes as a kind of confusion. And remember that this is a really simple example. And for more complex molecules, these kinds of differences can be larger. So that definitely also needed to change. And what we did in the new release was making the normalization procedure smart. This time, the optimization is weighted so that when we renormalize the pKa values, we try to make sure that the most important values for the key ionization pathway are as close to the original predictions as possible. And if you take a look at the new normalized values, you can see that almost all of them exactly match the original values except for the least probable dissociation step. So basically, we redistribute errors to the least probable stages. And as a result, if we compare the deltas, the calculation deltas with 2022 and 2023 versions of Percepta, we can see that in both log D and positive form fraction cases, the error has essentially gone. It's now back to the level of rounding errors. And so to summarize what I have presented here, I can highlight the following points. First of all, the current release not only improves pKa prediction performance, both in terms of accuracy and in terms of speed, but also resolves certain technical issues associated with previous algorithm versions, such as normalization error, and so on. And the improvements apply not only pKa, but to other pKa-dependent properties, such as log D and log S. And these, in turn, are used to predict a lot of ADME endpoints. As in our program, we use mechanistic models to predict intestinal absorption, blood-brain barrier permeability, pharmacokinetics, and so on. So these properties also have quite a lot to gain. So overall, the discussed updates make Percepta version 2023 a really significant step forward over the previous versions of the software. And of course, we are committed to improving further. And if you measure pKa in your company, and you're interested in these collaborative projects that I have discussed in my presentation today, you are always welcome to reach out to our team, and maybe you could also participate in such a kind of project in future. With this, I would like to thank you for your attention, and I'm looking forward to any questions.